Okay, let's start. So I'm Sasha Raklin. I'll be teaching this lecture. Then Lorenzo will continue for another 4 lectures or so. And then I'll take over again after a few more lectures from various people. And then I will be doing lots of statistical analysis, sample complexity analysis, which is the second part of this course. I will try to make everything as painless as possible to the extent that you'll learn some cool techniques for sample complexity, figuring out sample complexity of various methods without too much pain. That's the hope. Okay, so Lorenzo couldn't be here today. He went back to Europe. You'll have to learn a Russian accent. And I know you got used to the Italian accent, but he said he couldn't. I cannot take this. No, this American coffee. It's horrible. So he went back to Europe to have his coffee, and then he'll be back on Wednesday. So meanwhile, if there is something you don't understand, please raise your hand. I will talk today about optimization. I don't always start with history when I teach machine learning, but when I do, I start with Babylon. So we'll talk about what happened in Babylon in roughly 1800 BC. As you know, machine learning is mostly based on formulating an objective function with data involved and then running some optimization method. Yes, so everyone is familiar with this concept. It's not all of machine learning, but a lot of machine learning can be viewed as, let's write down an optimization objective. Let's use our knowledge of statistics probability to know which objective is the right objective. And then once we write down this objective, let's optimize it, right? So numerical optimization is a big part of machine learning, and of course now we're running optimization on things which you shouldn't be able to optimize, like neural nets. But before neural nets, let's start with Babylon. So Babylonians had a kind of a machine learning problem in mind. They wanted to calculate a square root of a number. So they took a number, let's say I don't know, 39. This is my x, and they wanted to know what is the square root of x. Can you see from back there, or should I write bigger? Good, okay. So they wanted to learn this square root of x, right? And so what do you think they used? How would they do this? Well, imagine you're in Babylon, it's 1800 BC. What do? You make a guess and you iterate. That's exactly right. And so this is kind of, you set up an optimization problem of some sort, or you set up a method that will converge to the right solution. Pretty much this is what we do now, right? We write it down, we come up with some iterative method and hope that it gives the right answer. So what did they do? They started with some initial guess W, let's call it W1. Let's say, okay, square root of 39, well, let's take it to be 100, right? A good guess. And then iterate, let's take W2 to be an average of W1 and 39 over W1, okay? Now imagine that you've guessed correctly. Imagine that you, by chance, guessed correctly W1 to be square root of x. Then this will stay at square root of x, right? It will not move. Otherwise, one can show that this improves. So then you do W3 to be average of W2 and 39 over W2 and so forth. And this is how you get a square root of a number. So this sequence w1, w2, and so forth converges to square root of x. Okay, seems a bit strange. Let's go forward by that many years to Newton. What is called a Newton method is the following iteration. So suppose you have a convex function f of w. Let's say it's a convex. And now you take w1 to be, let's say, well, something. Okay, that's your starting point. And now you iterate. W2 is equal to W1 minus, and let's do one dimension. So this is in one dimension. W lives in R. Minus the inverse of the second derivative at W1 times the first derivative at W1. Okay? This is called the Newton method. So let's try to run this Newton method on a parabola. Suppose your f is in fact a parabola. F of w is equal to a w squared plus bw plus c. What would happen to your iterates? Now you start with some initial guess for w1. And let's try to calculate w2. W2 is equal to W1 minus, so what is the second derivative of my function f? 2a. Good. Thanks for helping. 2a inverse. What is the first derivative? 2aw plus b. Yes? Let's expand this. 2a cancels for the first term. You get w1 minus, oh, this is w1, sorry. You get w1 minus w1. w1 goes. And what you get is b with a minus over 2a. Which is the minimum of this parabola, if you remember 4th grade? 3rd grade for some? No? Okay. So the moral of the story is you have a parabola. And you're starting at some initial guess. W, you guys cannot see it, okay. Do it here. You have a parabola. This is your space W. You start with some W1 here. And this is your value of the quadratic at this point. But now you use the first order information, which is the derivative, and the second order information, which is the curvature, which is just 2a for our case, right? To go directly to the minimum. So you go far enough to go to the minimum of this function, right? Because it's a quadratic, you know exactly how far you need to step so that you just hit the minimum. Right? Is it clear? No matter where you are sitting on a parabola, you know which direction to go to get to the zero and how much it's curving. And because it's a quadratic, it's curving the same amount everywhere, right? so that you just hit the minimum in one go, right? Is it clear? Is there anyone who is confused about this? Please ask. No? Okay. So the bottom line is this Newton method, as written, converges to the minimum in one step, which is amazing, right? Most of the time, we don't have optimization algorithms that do one step. You have to do many, many steps, right? But in this case, for a quadratic, it's converging in one step. I should say it converges to minimum in one step for a quadratic. Okay. So, can we see this as a Newton method? Well, let's see. What are we trying to get here? We're trying to find a number which is approximately square root of 39, square root of x. So let me erase this part. So we can write the question that Babylonians were asking as, can we find a zero, find a zero of g of w is equal to w squared minus x, right? Find a root. And if you can find the zero of that, then you found the w, which is equal to square root of x. Yeah, we're okay with that? Now, finding a zero of that function, what's the relationship between finding a zero of a function and finding a minimum of a function? The Newton method finds a minimum of the function. We are looking for a zero of the function. So one can be seen as finding the zero of a function. The other one is seeing zero of the derivative of the function, right? If it's a convex function, you're looking for a zero of a derivative. So the only change is that we have to work with one more order. So you can make it into w cubed divided by 3 minus wx, and then try that. Or let me just rewrite this. This thing becomes w2 is equal to w1 minus g prime of w1 inverse times g of w1, right? And if I didn't make any mistakes, right, so g is like a derivative of f, right? So let's try to do it. w1 minus, okay, the derivative of, this is inverse, sorry, inverse. The derivative of w squared minus x is 2w. So it's 1 over 2w1 times the function itself, w1 squared minus x. Yeah? Looks right? And that should give you this iteration. Is everyone okay with that? Any questions? You want to write this more carefully. 1/2 W1 plus x over W1. Except here you're going to iterate this. So, because the function is not quadratic, in fact, the f you would get should be cubic, so it will not converge in one step. So this is suggesting that the Newton method should be written as an iterative procedure where we replace this with t plus 1, this with t, this with t, and this with t, right? And this is my iteration, and then t goes from 1 forward, right? So Babylonians were doing Newton's method. Yeah? Good? Okay. We got Babylonians, and we kind of got Newton method. Let me describe the iteration of the Newton method for higher dimension. So what does this iteration for the Newton method, what does it become for not a one-dimensional function, but a function on Rd? So let's say f is convex on Rd. So what would be the iteration? You start with some W1. That's your initial guess. And then Wt plus 1 is equal to Wt minus, so the second derivative becomes a Hessian. Let's write it this way. I think Lorenzo used H for the Hessian. It's just a matrix of partial derivative, right? Everyone knows what the Hessian is. It's just a matrix of partial derivative ij. F at Wt. Now this is inverted. And let me just assume now that it's invertible. Okay, so I'm going to assume that this matrix is invertible. Times the first derivative, which is the gradient. That's the gradient. So this is a multidimensional Newton method. Any questions about this? Simple. So this is a Newton's method in multiple dimensions. Of course, it requires you to invert a matrix, which is painful. But what you know is that it will get in one step to the minimum of the quadratic if your function happens to be a quadratic. And so if your function is kind of like a quadratic or has the nice smoothness properties, you can expect that it converges quickly, right? In general, for a Newton method, one puts a scalar here, which is not 1, and that you can tune like a step size. But for now, we're just going to consider this particular form. Just keep in mind that when you look up a Newton method, you would get something slightly more general. Okay. So one thing that I guess I missed here is we're going to now apply this to recursive least squares. Recursive least squares. So let me remind you the problem of least squares. You want to minimize a sum of yi minus w transpose xi squared, minimize over w. And I'm not putting 1 over n because it will play no role in our discussion. Minimizing it with or without 1 over n doesn't matter, right? I'm going to write this for simplicity as a norm. So this goes from 1 to n as a norm of the y vector, this is my capital Y, minus xw squared. So that the meaning of this is that X is a matrix of n examples with rows being xi transpose. So these are the rows are the examples. And then I'm multiplying it by a W vector. And then I get out a n by 1 vector of the Y values. So this is a vector. And then I take a Euclidean norm, which is just sum of squares, which is exactly what this is doing, right? So nothing new. This is what we did, or what Lorenzo did. Of course, much more eloquently than I do, and with a much prettier accent. But the essence is the same. Okay. So I want to now connect the Newton method to least squares. Okay. Why? I think it's nice. This is a quadratic. So you can start with some point on this quadratic surface and then try to find the minimum. Right? It's a quadratic. Let me spend maybe 2 minutes talking about the geometry of this. Suppose you only had one example. So you have y minus wx, just one example, x1, y1 squared. This function in multiple dimensions, and this is only for those who have more geometric kind of intuition. I know people have very different intuitions, and some are better just numerically, some like to visualize stuff. I work with someone, I've been working with someone for a very long time, and whenever I try to draw something, the person goes, no, I can't, I don't understand what you're drawing. Right? Just give me math, right? And another person says, or like me, for instance, if I cannot see it, cannot visualize it, I don't really understand it. So the way to visualize this is, it's like a trough, right? So there is one dimension in which there is curvature, and then in all the other directions, it is just flat, right? Just like a gutter of a house, right? How do you see this? Well, if you take W to be perpendicular to X, then the value of changing W in that direction perpendicular to X, there is no change, right? So it's just flat. So this whole function is flat in that direction. And there are many directions like that. There are d-1 directions, right? So in most directions, it's just a gutter. And in one direction, which is the direction of the xi, you have exactly the parabola. So it's just a parabola in one direction, and then stacked together to make a gutter, right? So that's the way to visualize it, if you like. And now you're adding n of them. So you take this gutter, and then like that, and then like that, and like that, and like that. So at the end, it's going to be a quadratic, right? Because when you add two quadratics, you get a quadratic. But there might be some directions where it's still flat because you haven't really covered all the directions, right? And this whole issue of invertibility that Lorenzo talked about is really about, have you covered all these directions or not, right? Because if there is a flat direction, then there is no curvature in that direction, there is no change in that direction, and so the Hessian is 0, right? The eigendirection there is 0. Okay, so that's a little bit about the geometry, and for some of you this will make it more confusing, for some of you it will make it less confusing, but I think people really think differently. Okay, If you want more, I can give you more geometrical intuition and so forth. Okay, so right, so let's just try the Newton method on this quadratic, right? So now f of w is y minus xw squared. Okay, I put the error that it's a vector, but I didn't put it on the w. Let me just not put it. It's clear from the context that it's a vector, right? That's an n-dimensional vector. This is n by d and d by 1. Okay, so let's calculate the first derivative, the gradient of this function at any w. I can calculate it at any w. So 2 comes down. Now I have to take the derivative of this as a, I have to take the derivative of the inside, right? With respect to w, so that becomes x. In fact, it becomes x transpose, because this is the gradient lives in the d-dimensional space. Now it's 2x transpose, but then there was a minus. Right, so it's a minus 2x transpose times just the value, right? So that's a y minus xw. So if you remember your chain rule from calculus, this is what it comes down to. It's always good to check the dimensions when you take these derivatives, that you've got the dimensions correct. How about the second derivative? Well, let's see. So if I were to open this up, open the square, right, I would get a cross term that vanishes under the second derivative, right? All the first order terms get killed. All the constants from here get killed. The only term survives is the w times w transpose xw, and the second derivative of that is just x transpose x. Except there is a 2, because I have to, it's 2 times what's the derivative of what's inside, right? Yeah. So what would the Newton iteration be? I start with some w1, something. What is my w2? Not in terms of the tax w2, but this w2. W2 is w1 minus 2x transpose x inverse times the gradient. It has a minus, so I'm just going to put a plus here. 2 x transpose y y minus xw. So the 2 gets killed, right? 2 gets cancelled. It's 2 and divided by 2. And so it's just w1 plus x transpose x inverse. Oh, this is w1, sorry. This is w1. X transpose y minus xw1. This is my iteration. So if I started with w1 equals to 0, my 0 vector, what do I get? w2 is 0 plus remains, gets killed. X transpose x inverse x transpose y. which is the least square solution. Yeah, so we know this. So it checks out. So the point is, you've got a quadratic. Now, it's in d dimensions, so you have to be careful. But essentially, you start with 0. W1 is equal to 0. This is a center of coordinates. And you've got some value. But then you can make just one step of Newton, and then you get to the minimum. In fact, you can start from any point and make one step of Newton, and you get to the minimum, because Newton converges in one step for quadratics. Okay. Good? Okay. So this is just to verify that you do get least squares out if you start from 0. Sorry, if you start from any point, you get least squares out, but you don't have to have any W1 in this calculation. Is that clear? Yes? Good. And this brings me to the next subject, which is, what if data comes in an online fashion? What if you've computed your solution, your least square solution, with t points, but now t plus 1 comes, right? Do you have to resolve the whole thing, or can you make small, quick, cheap adjustments to get the new least square solution, right? So you've got your data, you fitted the least square line, right? That this is the picture that statisticians would have. And then there is one more point. Can you just adjust this a little bit? Or do you have to solve the least squares from the beginning? And you can already see that we're just going to do a one-step correction to this. And just see what kind of storage we need and what kind of computation we need to keep this going. So the next subject is, let's call it recursive least squares. Okay, so suppose you start with W1 equals to 0, and then let WT be the least square solution with x1, y1, xt minus 1, yt minus 1. This is the way that I chose to index my variables. Wt will be the least square solution for data up to t minus 1. Okay. So let's see what Newton's method would give us. So we know that we should be able to get, we can get Wt plus 1 from Wt with 1 Newton step, right? With one step of a Newton method, right? Now, why do we know it? Well, we saw it in one dimension that it gets to the minimum, and trust me that in multiple dimensions it will also get to the minimum. Yeah? And I'm going to assume that this matrix is invertible, so that I can, this x transpose x is invertible, which is actually not true in the beginning, right? Until you fill up all these directions, it's not true. So either assume that you're starting after it's invertible, or add a regularizer, lambda times the norm squared of w, and nothing will change in this picture. It's also a quadratic, nothing will change. So if you're worried about invertibility, invertible x transpose x or not, solution, just replace in everything that we do, replace x transpose x with x transpose x plus lambda I, which, as you know, is the solution when you add a lambda norm of w squared to your objective, to your least squares objective, then it becomes a regularized least squares. Okay, so let me do the following. I'm going to say that Newton method gives me W1 minus, I'm going to call it CT inverse instead of X transpose X inverse, because I want to allow this possibility that you take regularized least squares. So CT inverse is going to be, so CT is either X transpose X or X transpose X plus lambda I, if you started from regularize these squares. So this is not, sorry, this is not 1, this is T. WT minus CT inverse times the X transpose Y, right? Sorry, times the X transpose Y minus XWT. So there is something here that is not exactly correct, which is it's not the full X, right? We're doing the incremental version of this method, and this X only has data up to T, right? So let me subscript this with T, and this with T, and this with T. And let me check that this is coinciding with what I did. Yes. So here xt is a matrix x1, I guess transpose if you want to make it a row, up to xt transpose. And yt is similar, defined similarly. Yes? So the 2 cancels, right, with this 2. So I'm just going to ignore it then. And yeah, minus is correct, right? Yes, thank you. See, when Lorenzo was giving lectures, I was correcting him. But now, maybe he can travel back in time and correct stuff. If you hear something in your head, it might be Lorenzo. Yes.
Can you just clarify what you mean? So beforehand, what we were doing, we had a set data set.
Yes.
And then we were talking about iterating through, and it turns out you can do that in one step.
Yes.
Right? Over here, it's a very different iteration, right? Like we're solving a different problem.
Exactly.
So the T's are not what you were talking about T's before.
Exactly. Very good point. Let me. I went a bit too quickly. Let me try to clarify this point. Are you a picture person? Can I draw a picture? Good. So at time t minus 1, you've got the data x1, y1 up to t minus 1, yt minus 1. This defines a quadratic. And wt is the one that minimizes this quadratic. Yes, just by the way that what I wrote here, right?
You're going to call wt minus 1.
So I'm going to call it wt because wt is the least square solution with that. It's the minimum, right? Now, when I add one more point, so then add one more of these troughs, right? One more gutter to this. So then we add xt transpose w, and we wrote it like this. This perturbs this objective. Now it becomes this objective. And now wt is no longer the minimum. So wt is now wt is now gives you that value, but now we're going to get wt plus 1 as one step on this new purple objective. And that's what I'm writing, right? So what I'm writing is a Newton step. I don't care how wt was obtained. I know that whatever it is, in one step, I should be able to get the correct wt plus 1 because it's a quadratic. So I'm just writing the Newton step on the new objective, the purple objective.
So I'm assuming we're going to move well beyond sort of the Newton method because there's something clever you can do about, okay, we knew what the previous one is and now we added that and we don't have to reproduce it.
Exactly. That's what I'm going to do. No. Yes.
So if you didn't have this one step, guarantee that the convergence group would be either more slow or non-existent.
Right, then they would have to run it until it converges, right? And then you add one more point, then run it again until it converges, right? Yep. And now, exactly what you were saying, what is a clever thing here is the geometry again. And it's the fact that the residuals are orthogonal to the data, but only to t minus 1. So what do I mean by that? I guess I erased it. Let me call the f of t of w to be the objective yt minus 1. So let me put minus 1 here. Minus xt minus 1 w squared. Then wt minus 1 implies that this gradient is 0, the gradient of this, right? Because wt minus 1, sorry, wt implies that if I take a gradient and then plug in wt, it has to be 0. What is that? So gradient of ft minus 1 wt is equal to 0 means that, let's do it again, 2, which doesn't matter, xt minus 1 transpose yt minus 1 minus xt minus 1 wt is 0, right? I just rewrote the gradient that was sitting exactly here at this point, right? This is the gradient. These are the residuals. These are called residuals. This is what statisticians would like to be roughly normally distributed, right? Otherwise, all hell breaks loose, right? These are the residuals, and the residuals are orthogonal to the column space of xt minus 1, right? In some sense, what this means is that you've squeezed out everything you could from the data in terms of the linear fit. Everything else is orthogonal, right? So then this becomes, now this was a matrix, remember? It was a matrix. So this becomes, well, xt just has this appended one extra column or row. Xt has one more row appended. And that's the only thing that survives. Everything else is killed. So you can write this as wt plus ct inverse. Now the little xt transpose. No transpose, sorry, because xt is a column, and then no transpose. A yt minus xt transpose wt. Right? This is d by d. This is d by 1. That's correct. Yeah? This is called recursive least squares. Why is it recursive least squares? What do you need to keep in memory and what do you need to update? Nothing about the past data here, except I have to tell you how to update the CT. Right? Any questions? We all agree that if I tell you how to update CT, we're done. So updating CT from, or inverse, from CT minus 1. CT minus 1. So this is where the standard Sherman-Morrison formula comes in. Is it clear with this picture what's happening? Yeah? It's like you're tracking an objective. Your quadratic objective keeps shifting, but you have to just make one little adjustments, one little steps at time iteration to keep doing the least squares, right? Instead of resolving the whole thing, you just keep making small changes and you're tracking this quadratic objective. Yeah? Questions? Yes?
What happens if we don't start from W1 equal to 0?
Actually, that doesn't matter, right? Because that doesn't matter, right? It's only the first step will have that W1, and then the update will have the W1 in there. But then after that, it's all least squared, right? Because we know in one step it converges to the minimum, right? So only the first step will be affected in that way. Yeah. If you start with W1, which is something else, W2 will be W1 plus the update with the W1 in there, right? It's not going to be this.
Actually, if you look at the formula that was there before, W1's cancelled.
W1's cancelled, right? Okay, so updating. Okay, so this is the Sherman Morrison 2R Morrison formula. And if your brain is connected to Wikipedia, you're better off. I have to remember always. So it's A plus, A is a matrix which is assumed to be invertible. So A is an invertible matrix. Then UV transpose inverse is equal to A inverse. This is also called the rank 1 update because this is a rank 1 matrix. So that's a rank 1 update for the inverse minus, and you get A inverse UV transpose. So A is square and invertible. Square and invertible. A inverse 1 plus, no. V transpose A inverse U. Is that right? I think that's right. Okay, so this is an example of our more general Woodbury inversion formula. This is just the simpler version of that. So what is CT? CT is equal to CT minus 1 plus XT transpose, right? Is that clear to everyone or not? You remember from the previous lectures, the X transpose X, that matrix transpose matrix, the data matrix transpose data matrix is just the sum of XT transpose. So the way that it gets updated is just by adding one more XT transpose. If you had lambda I in there, it just stays there, and this equation is still correct, this equality, right? So this is true both for CT, which is the sum of the outer products, and CT, which is the sum of outer products plus the lambda inverse, which is the regularized solution. Okay, so now let's apply this. CT inverse is equal to CT minus 1 inverse minus CT minus 1 inverse XT transpose CT minus 1 inverse divided by 1 plus XT transpose CT minus 1 inverse XT. And now if you multiply both sides by XT, because I can keep track of, well, no, I need to keep track of this, so forget about this. Well, let's just see what I need to keep in memory, right? So what I need to keep in memory is this matrix, CT minus 1 inverse. I never have to actually invert anything. I just keep it in memory, and then update the new inverse to be the previous inverse plus, so this is matrix vector multiplication, and that's just a square of that, right? So I can do it once. And this is matrix vector multiplication times another vector multiplication. So it should be d squared. If we get everything right, it should be d squared per time step. So update is order of d squared per iteration. Right. So memory requirement is d squared. Time requirement per iteration is also d squared. I never have to store my X matrix. Yes? As well. Yes. So I can just do this repeatedly, or I can try to play with a more general formula for this. There exists a more general formula, or I just do, 10 iterations of this with the 10.
But is there a trade-off there?
But trade-off with what? So with if there's like a faster, is it faster? Good question. My guess is that there is not faster than 100 times d squared. Just needs to be checked. It should be like a few lines to check. Yeah.
So this is just because, originally the inverse is of order of d cubed.
Yes, that's right.
So this obviously breaks down at some point when you get to a big matrix, because you just keep adding iteration by iteration, you're going to keep going this matrix.
No, but you would need d rank 1 updates. D times d squared is exactly d cubed. Yes. Okay, so this is what we would call an online method. It's a method that doesn't need to store previous data in memory. Everything that it needs to store is encapsulated in the W. W is like a sufficient statistic of the past data, right? And you just do something quick per time step, and keep tracking this moving target, right? That's an online method. Okay, good. Any questions about this? I'm gonna erase. Yes.
How did I get that for say t is equal to say t minus 1 plus?
By definition, because the CT is the right. If you write down the least squares objective, that this multiplier matrix is X transpose X. X transpose X is the same as a product of a sum of outer products of XX transpose. So X transpose is a matrix. So this is X transpose. This is a matrix. sorry, we had energy problems here. Right. Equivalent way to write G Lipschitz is that the norm, let's say with respect to L2 norm, the norm of gradient of f is bounded by G. Okay. So it doesn't get steep. The function doesn't get too steep, right? The norm of the gradient is bounded. And let's take this iteration, and let's assume that W1 is equal to, let's say 0. This is not important. And W star to be in the argmin of f W. So it's a minimizer. W star is the minimizer of the function. Okay, this is W star. And assume that the norm of W star is bounded by some number, say B. So this is just to kind of to place the function not too far from the origin, right? So assuming that you can place the function close to the origin. Then, if eta is chosen to be square root of t b g, blah blah blah, and we'll fill in what this blah blah blah. So we'll prove something, and then we'll see what that blah 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 is. Okay, proof. This is the first proof, right? This is the first proof we did in this class. We're doing in this class. Yay. Okay, many more to come. Let's write Wt plus 1 minus W star squared. This is like tracking how far we are from the optimum. Now this is equal to Wt minus eta gradient f of Wt. By definition, that's the gradient step. Minus W star. And because I promised only a few lines, Wt minus W star squared plus eta squared norm of gradient f at Wt squared plus 2 gradient of f at Wt, and the angle brackets is the same as transpose, right? The inner product. Or do you want the transpose? I can do the transpose. Transpose Wt minus W star. Why? Why is this the case? Because a plus b squared is a squared plus b squared plus 2ab. Eta. This is my first line. And now I'm just going to rearrange, which is actually the same line. I'm just going to rearrange things. Yes? Yes. Thank you. Good. Thank you. I'm going to rearrange things so that that minus becomes a plus. I'm going to bring it to the left side. And I'm going to bring this to the right side, right? So this doesn't really count as a line. So 2 eta gradient of f at Wt Wt minus W star is equal to Wt minus W star squared minus Wt plus 1 minus W star squared plus eta squared. Okay, I'm gonna now replace this norm by its upper bound, by g. So I'm gonna make this into an upper bound, and this is just g squared. And now I add this over t iterations. So add for t from 1 to capital T. That's how many iterations I'm gonna run of this gradient descent. So what do I get? I get 2 eta sum, right at here, 2 eta times the sum of gradient f at Wt and Wt minus W star is upper bounded. Now these things telescope when I add over t. It's like W1 minus W2, W2 minus W3, and so forth. They all telescope except for the first one and the last one. The first one is W1, which I assumed is 0, so that's 0, minus the norm of W star, and that's bounded by b squared, right? So now that's b squared. And the minus term I can drop, right? It's a minus term, negative term. Plus eta squared g squared. Now let me divide by 2 eta throughout. By the way, this should remind you of the Babylon thing, right? That's exactly how we got square root. We took 1 over something plus something, right? Yes? That should be a capital T, thank you. Nope, not here, this one. Thank you. And now, with that choice, you can check that this becomes bg squared of t. Yes? And let me divide by t now, 1 over t. Because this is for 1 to t. I'll divide by t, divide by t, and now this becomes divided by square root of t. This is really the same line. Right? But I claim that this is an upper bound on a f of Wt minus f of W star 1 over t. So why is that the case? Well, if f is convex, that means that f of Wt is less than f of W star plus gradient f of Wt times Wt minus W star. I guess I put this, the brackets, it's the same as transpose. This is true if you rearrange things, it's the same as, right? This is saying f of W star is above the first order approximation. The first order expansion. You can just read it off from this. If you've got W star here and Wt here, then this is saying W star is above Wt plus the first order expansion the gradient times W star minus W. And this is by convexity upper bounded by f of W bar minus f of W star, where W bar is 1 over T sum of W T, T from 1 to capital T. Okay, just by Jensen inequality. Jensen inequality means that this average goes inside of the convex function. It becomes a smaller quantity, right? Or the other way around. If you pull out the average outside of the convex function, it becomes larger. That's what this statement is. Yes?
They chosen the even to be the tightest upper bound.
Yes, I have. That is the right. That is the right. The tightest one. So the conclusion is f of W bar minus f of W star goes as bg over square root of t. In other words, for the average of the trajectory, the rate of convergence to the in function value, the rate of convergence is 1 over square root of the number of iterations. It's considered relatively slow, but if you take statistics into account, you don't really need to go too fast because there is randomness in the data. We'll spend a lot of time discussing this. That's why these simple first order methods became really popular, because you can it's a cheap method. You just compute the gradient of the function and you converge at the reasonable rate, especially with large amount of data. Now, I have 3 minutes and I didn't get to stochastic gradients. Okay, so let me do it in 2 minutes. If everywhere you replace, instead of gradient of f at wt, if you replace it with some vector wt, which is an estimate, an unbiased estimate of this, which is in expectation, this gradient conditioned on the wt value. So everything is now conditioned on the wt value, is equal to the actual gradient of the function at wt. If you've got this, everything just works. The same proof goes through. And that is what's called the stochastic gradient descent. The gradients don't have to be the actual gradients of the function. They just need to be correct in expectation, right? Is this clear at this point? Amazingly, everything goes through. This is the most amazing thing ever. You go in the direction which is actually not a gradient direction. You don't decrease the value of the function. You do something that's roughly correct in expectation. But it could throw you away. As long as in expectation, on average, it's the right thing. It's the right direction. And everything just works. So for this, what you need is that the expected norm squared is bounded by g. So you need the variance of this estimate to be not too crazy, right? And that's enough. Yes.
So in other words, as long as the variance is finite, right, it does
When-
not have an impact on the
That's right.
convergence.
That's right. So if the variance is finite, that number just appears in the convergence rate. It's amazing. Like this thing goes in all kinds of directions, and it gets to the right place. Right? That's called stochastic gradient descent. And if I could paraphrase a Twitter account, ML Hipster, who is Mark Reed in our community, he writes wonderful little tweets about machine learning. He calls it sarcastic gradient descent. Yeah, going in that direction will totally minimize the value of your function. Sarcastic gradient descent. Okay, we'll meet next time.
Tune up.